We now address the question, why are compounds aromatic if they have 4n plus 2 pi electrons, but not if they have 4n pi electrons? Okay, so to look at this, I would like us to review the MO diagram for benzene that I presented a couple of lectures ago. So in benzene, there are an even number of molecular orbital energy levels. There are 4 molecular orbital energy levels. So that means all of the molecular orbitals will be either bonding, if they are lower in energy than an isolated p orbital, or anti-bonding if they are higher in energy than an isolated p orbital. There are always going to be an odd number of bonding molecular orbitals because we put a single molecular orbital at the lowest possible energy. Okay, so in benzene there are 3 bonding molecular orbitals, and with 4n plus 2 pi electrons, that's 6 pi electrons, and that's 3 electron pairs. So there's also, no matter how big of an aromatic molecule you have, there's going to be an odd number of electron pairs if there are 4m plus 2 pi electrons. So the bonding molecular orbitals will be completely filled, and the anti-bonding molecular orbitals will be completely empty. Let us now contrast this situation with cyclooctatetraene. So following the rules for drawing MO diagrams, which is that we're going to put a vertex of our polygon at the bottom, there are going to be 5 MO energy levels. 1 lowest in energy, then 2, then 2, then 2, and then 1 highest in energy. This is, of course, assuming cyclooctatetraene were planar. We know it's not, but we have to consider what it would be like if it were planar in order to demonstrate that it's not aromatic. So the bottom 2 energy levels are going to be bonding, and the top 2 energy levels are going to be anti-bonding, just like in benzene. But now we have 2 more molecular orbitals in this middle energy level that we have to deal with. So this middle energy level, it turns out, will have the exact same energy as isolated p orbitals. These molecular orbitals are neither bonding, they're not lower in energy, nor anti-bonding, they're not higher in energy. So we call them non-bonding. So with a total of 8 pi electrons in cyclooctatetraene, we have to put 2 electrons into the non-bonding orbitals. We only have room for 6 electrons in the 3 bonding molecular orbitals. So the fact that we are populating non-bonding orbitals is not a problem in and of itself. The problem, as you can probably see from looking at this structure, is Hund's rule. Remember that from general chemistry? Hund's rule tells us that as we're filling orbitals, you learned Hund's rule about filling atomic orbitals, but the same rule applies to filling molecular orbitals. Hund's rule tells you that when there are 2 or more degenerate orbitals, orbitals that have the same energy, we must half fill each one with electrons before we compare electrons in any one orbital. Okay, that rule is basically saying that, electrons don't like each other very much, and they're not going to pair up, put 2 negative charges into the same orbital and leave another orbital with the exact same energy empty. You're going to half fill each one first. And here's where the problem shows up. So the 2 electrons in the non-bonding orbitals would be unpaired. So if this planar structure were correct, the molecule would actually be a diradical. It would have 3 pi bonds and 2 unpaired electrons. That would be an extremely unstable situation. Therefore, this molecule is actually called anti-aromatic. To avoid anti-aromaticity, cyclooctatetraene adopts a non-planar conformation, the tub-shaped conformation that we saw in the last lecture. Therefore, the double bonds are true double bonds and the single bonds are true single bonds. Cyclobutadiene, the other molecule that we considered in the last lecture, must be planar. It's a four-membered ring. It doesn't really have the ability to go tub-shaped, at least not with two double bonds in the ring. So it cannot escape the fate of anti-aromaticity, and therefore it has a fleeting existence. So that is why cyclobutadiene would be so incredibly unstable. Now, what about larger ring sizes? Well, in the last video, we alluded to the fact that 10-annulene, the aromatic system, it would be aromatic based on its Huckel number, does not exist. And I had said that if the molecule were all cis, there would be too much angle strain if the double bonds were all cis. There's actually another possibility that I have to introduce at this point because I'm going to use this in the larger rings that I'm going to tell you about next. And that is, you could have a 10-membered ring with two trans double bonds. In other words, naphthalene, take out that central bond. However, that would eliminate the angle strain, but the way I have this drawn does not really show you what those two hydrogens would really have to look like. In order to have 120-degree bond angles at those central carbons, those two hydrogens would actually be bumping into each other and trying to occupy the same space. So you can't actually have a 10-membered ring with two trans double bonds. So that's why 10-annulene does not exist, despite the predictions of Huckel's rule. But when we go bigger than that, we open up the ring enough that there's room for hydrogen atoms to be at the center without bumping into each other. So this is the structure of 14-annulene, the 14-membered ring with 7 double bonds in it. And as you can see, 4 of those 7 double bonds are trans. This molecule exists, it's very stable, and it shows the same aromaticity properties that benzene does. And its molecular orbital diagram looks as follows. So we have 14 pi electrons, and they're going to go into the 7 lower energy bonding molecular orbitals. So the 7 bonding molecular orbitals are all filled. The 7 anti-bonding molecular orbitals are all empty. And this molecule basically looks like benzene, except it just has more orbitals and more electrons in it. Going one step further will take us to 18-annulene, another very stable aromatic structure. And its molecular orbital diagram is going to look very similar to that of 14-annulene, except we now have 4 more molecular orbitals. There are 18 pi electrons. So in this case, there are going to be 9 bonding molecular orbitals, and those 9 bonding molecular orbitals are all going to be filled, and the 9 anti-bonding molecular orbitals are all going to be empty. You can keep going bigger and bigger with your ring sizes, but that would not really get us anywhere. It would just show that the rule holds, which it does. What we need to move towards in the next couple of videos is an examination of aromatic ions, which will get us into what about rings with an odd number of carbons in them. So you can have those situations, but then more importantly, we need to get into the topic of aromatic heterocycles. What happens if you put oxygens or nitrogens, or sulfurs for that matter, into the ring? Which ones are going to be aromatic and how are they going to differ from each other? Okay, so that's where we're going to go next.